Well, hello, everyone. First of all, I would like to thank the conveners for inviting me to join this exciting workshop this week. Also, I would like to thank NASA for funding part of the research that I'm going to be presenting today. And of course, multiple discussions and collaborations with different colleagues from different institutions and countries. I would like to start first telling you what was the first thing I heard during the first volcanology class I had in my life. That was during my PhD at the very beginning. So that was something I heard from Chris Newhall, who is now retired. And he told us, volcanoes are like champagne bottles. And honestly, I was pretty disappointed because I hate champagne, okay? So, and this is a true story. I was thinking, hopefully I will not hate volcanoes as well in a few weeks, no? So moving forward, I started to read papers to learn about the influence of volatiles, the importance of understanding how gas is behaving. And I was getting more and more excited. And the climax came when I found this paper on Guinness beer and volcanoes in 1996. So I don't hate beer, so that was a good sign. So the first thing that I learned from these papers I read at the beginning of my PhD was that definitely volatiles can control how volcanoes work. And the second important conclusion is that, well, volcanologists really want to have fun. So today in this talk, we are going to try to have some fun while learning the importance of volatiles to control the dynamics of volcanoes. So in this slide, I'm going to show a very brief scheme on the physics-based scheme of the physics-based overview from melt to air. With this, I mean that we want to understand what's happening when gas exsolves and volatiles exsolves, forms a gas phase, and what happens when it migrates towards the surface. So we are going to be talking about exsolution and how this can affect, in particular, the rheology of the system, the rheology of the melt. So you can find this plotting, for example, in this review paper by Oppenheimer. You can see the influence of the dissolved amount of water vapor with the viscosity. You have the water vapor, you have water in the horizontal axis, and in the vertical axis, you have the viscosity. And this is for different types of melts. So what one can see is that if you reduce the dissolved amount of water by 1% or so, this can produce a change of up to 1 to 2 orders of magnitude in the viscosity of the melt, depending on the type of melt that we are interested in. However, this is not the whole story, because if we want to understand how volcanic eruptions evolve with time, we need to understand the rheology of the magma itself, not only the rheology of the melt. And the rheology of the magma implies that we need to understand what's the viscosity of the magma, which is the mixture of crystals in gas phase and melt. So one can understand how this exsolution affects viscosity by looking at this plot. In the horizontal axis, you have the volume fraction of bubbles or crystals, and in the vertical axis, you have the relative viscosity is relative to the melt. And we can understand this in terms of a dimensionless number, which is called the capillary number. Are you familiar with this number? Okay. So basically, with this dimensionless number, we are going to be comparing the viscous forces and the surface tension forces. So if you have a capillary number which is much lower than 1, that means that surface tension forces dominate. And that means that bubbles are basically spherical. In this case, we observe that when we increase the amount of bubbles in the mixture, we are going to increase the viscosity of the magma. However, we find a completely different behavior if we have the opposite scenario. If we have a very high capillary number, in such a case, the viscous forces dominate over the surface tension forces, and bubbles are not spherical anymore. They are kind of ellipsoidal. So in this case, we find that when we increase the amount of this gas phase of these bubbles in the system, we are going to decrease the viscosity of the magma. Also, we need to keep in mind that the shape of these bubbles are going to be changing depending on the shear rate, depending on how magma is moving, depending on the interaction of this magma with the walls of the conduit, for example. So that means that, as you can imagine, there are many different feedback processes here, and understanding the evolution of the rheology with time during an eruption is something that is not straightforward. There are many things to understand. There are a few more things. Now we are going to talk about different types of degassing, and I'm pretty sure that this will come out also at some point during this week. we have closed system degassing, and this is defined as the degassing of the solution of these bubbles when the gas phase cannot move independently of the melt. So basically the whole magma is moving and nothing is happening. This is the kind of the simplest scenario, because that means that we can assume a thermal equilibrium between the gas and the melt, and therefore we can understand many of the properties of this gas assuming this equilibrium. However, there are still many important processes going on even during equilibrium. We can have fragmentation, we can have explosive eruptions, and this happens during closed system degassing. Now I'm showing a few the results of some experiments that were performed by Namiki and Manga in 2005, where they explore what happens with the bubbles in a viscoelastic fluid when they change the pressure of the system very quickly. So if this pressure changes quickly, you can lead, or we observe that we have fragmentation in the system. However, if the compression is slow, in such a case, we will see that basically nothing happens. Gas is going to expand. You may have the interconnected vesiculation, gas can escape, but you will not have fragmentation. So that means that in order to produce volcanic explosions, you probably are going to have a quick expansion of bubbles produced by a quick depressurization of the system. And I have a question for you. I have been talking about nucleation, about expansion of bubbles for this fragmentation problem. And these are bubbles which are already in the mixture and expand due to the depressurization of the system. But what happens with other processes like nucleation and diffusive growth? What do you think? Do you think that that will play an important role in the explosive eruptions? Well, it's a matter of timescales. That depends on the timescale. If we are talking of the initiation of a volcanic eruption, probably that's not going to be that relevant. The most important thing is going to be the expansion of the bubble that is already formed in the mixture. However, if you are talking about sustained eruptions, that means that timescales are going to be longer, and therefore bubble growth because of diffusion and also nucleation are going to start to play an important role. Then we also have other type of degassing. So now we have open system degassing. And if you just compare with the previous case, again, we have my favorite cartoon here. So gas is able to move independently of the melt. So that means that exploring this from models is much more difficult because we cannot assume equilibrium. And we have what we call gas phase separation. So it is thought that gas phase separation can explain different regimes of eruptions that we have in volcanoes. For example, it is thought that slag flow is able to produce strombolian eruptions. So probably, are you familiar with slag flow? Do you know what that means? Okay, so this is basically the formation of these cylindrical bubbles in these conduits. We can also have some other important phenomena going on here associated with gas phase separation. For example, we found a few years ago that in the continuous release of gas during quiescence of a volcano, this can produce significant pressure changes in the magma plumbing system that can eventually affect the long-term evolution of a volcano. For example, with typical values for the degassing rates, we found that these depressurizations can reach values on the order of up to a few megapascals after a few years of degassing. Interestingly, Shreve et al. Just 1 or 2 months ago, they published this paper where they applied this model for the first time to a real volcano, because I didn't do that in the original paper. And this is for Ambrym volcano. And it's interesting to see how the authors found a very good way to explain their data based on this model. Then when we talk about gas phase separation, that means that we also want to understand how eventually gas separates from the magma and reaches the surface, reaches the air. Well, if we have a lava lake or if we have a lava flow, we can consider that the bubble is moving directly from the melt into the air. But things are generally a bit more complicated because we have a country rock. That means that the gas is escaping via permeable flow through the crust, or is escaping via permeable flow through the conduit or through a porous dome, for example. And that's going to be the main topic of the next slides. We are going to be discussing a few examples of how the permeable gas flow through the crust can explain some of the monitoring signals, can provide an explanation to some of the monitoring signals that we observe in active volcanoes. And in particular, I'm going to be talking about gas-driven volcanic tremor and long-period seismicity. And I will be talking as well about gas-driven low-temperature thermal anomalies. Okay, so I will start about the first one, gas-driven volcanic tremor and long period seismicity. And first, let me show what is the motivation behind this research. So we know that active volcanoes have probably active magma reservoirs. That means that there are many different physicochemical processes going on in the subsurface, like crystallization and like the exsolution of bubbles and the formation of this gas phase. This also relates to the excess degassing paradox that says that the amount of volcanic gases emitted from volcanoes greatly exceeds the amount of volatiles that were dissolved in the erupted magmas. This also, in fact, this is telling us that in between eruptions, during quiescence, we can expect to have a significant amount of gas phase already formed in the magmatic system. So this leads to the key question that motivates this research, which is what happens with the excess of gas phase before an eruption? What happens with that gas? So there are different geophysical, geochemical, and modeling investigations that suggest that gas can accumulate in different parts of the shallow plumbing system. This could be at the top of a magma reservoir, this could be somewhere in the hydrothermal system, this could be beneath a permeable dome. And this leads to the, well, this is in fact the hypothesis that we use, the working hypothesis for this research. So at this point, we don't care much about where these gas pockets actually are in the system, but we want to understand the mechanism itself. So we want to understand what happens if we have a gas pocket or just a fracture which is filled with gas, what happens with the pressure of that fracture or that gas pocket when gas accumulates temporarily before it moves upwards, controlled by the permeable flow of the system. I'm not going to explain this in detail, but just let me highlight that here we can solve the transport equations, combining the Navier-Stokes momentum equation for porous media, assuming ideal gas law. Again, I'm not going to explain the details. Then we can combine this with mass conservation, and we can also assume some hypotheses for the input of gas into the gas pocket. So the important point from this analysis is that one can see that when you integrate all the equations all together and you simplify the problem, because otherwise it would be impossible to solve it, and there's some realistic simplifications, we find that the evolution of the pressure in those gas pockets are controlled. The dynamics is controlled by the pressure, by the equation of a linear oscillator. And the equation of a higher the linear oscillator, and that implies vibrations, implies resonance, implies periodicities, implies things that we typically observe around volcanoes when we explore seismic data. Also, if you take some other simplifications, assuming a very thin cap, like for example, the accumulation of this gas layer beneath a permeable dome or right below the crater of a volcano, one can find that this equation simplifies to the simple damp harmonic oscillator driven by an external excitation, which maybe this is not telling anything to you, but this is just the equation of a spring. And in physics, we are experts in exploring the equation of a spring because it's probably the only thing that we can solve. The interesting point here is that we can find also an analytical solution for this pressure evolution, and we can start to link different signals with different properties of the very shallow subsurface. From here, one can find the vertical ground displacement. Again, I will not explain the details, but just let me highlight that we have three different factors here. We have a resonator factor that accounts for permeability of the cap, porosity, size of the gas pocket, forcing factor, which accounts for how the gas is being supplied into this gas layer, and the properties of the medium, which is basically where the seismic waves are going to propagate from the source to the receiver. So we see that with this kind of signals, we can generate this synthetic ground displacement that can explain different features that we observe in nature, like periodicities that we find in LP signals, long period signals, or periodicities that we find in tremor signals. This is just the amplitude spectrum, which is showing a very well-defined periodic vibration. So just let me show one very quick example of how one can use this model to better understand the evolution of a volcanic eruption. So this is the work that one of my students is doing, Kalman Kim. So this is the eruption at Gracie King volcano starting last summer. So we have a very beautiful dome that is growing in the volcano. And basically from this model and taking into account or accounting for these LP events, we can use the model to run some inversion. This is the normalized amplitude spectrum, where in blue you can see the data and in red you can see the model. And from here one can infer some parameters like the gas temperature, and the radius of the dome, or the mean gas flux. So that means from seismicity, we can start to link to some of the parameters that eventually we should be able also to calculate independently, and therefore to compare with this model, with this impression. So I think I would like to highlight is that we see that the radius of the dome is on the order of magnitude that we observe from satellite data. So the take-home message from this few slides is that we find that the permeable transport of gas from magma bodies to the surface can produce seismic signals. But of course, this is not the only model. There are many other models, because gas, basically, when gas is moving, it can produce so many different things. For example, we have this paper by Jelinek and Verkovici in 2011, where they proposed that some of the tremor signals or tremor properties can be explained by the resonance of this magma foam that is formed around the walls of a volcanic conduit. And there is also a very recent paper by Laura Spina et al. In I think last month came out, where they proposed that some of the properties of these tremor signals can be explained by the motion of or transport of the gas from one gas pocket to another gas pocket inside the volcanic conduit. So as you see, when gas is moving, it can produce many things. Okay, so with this, I'm going to move to the last part of the presentation, which is about the gas-driven low-temperature thermal anomalies. And I will start with, again, talking about this thing, banana beer. Banana beer is a very popular drink in Ethiopia and Congo. And after we got this paper published last year, I received an email from Chris Newhall, who told me, take a look to this paper, because we did some surveys in Congo after an eruption, and we found some interesting things. I went through it, also through some personal documents that Chris sent to me. And what is interesting is that after this eruption in 2002 in Nyiragongo volcano, there was a survey where different colleagues from USGS and also from Europe, they went to Goma city close to Nyiragongo. They made a survey. They were asking questions to the peoples living nearby. And some of the reports are here. Villagers reported abnormal occurrence of warm ground in several villages around the volcanoes. Also, they reported that the maturation time of bananas used to make the beer was reduced to 2 days, which is an important thing. And also, they reported that these observations came from widely separated areas. So this suggests that apparently volcanoes may show low temperature thermal unrest over large areas before an eruption. Why am I showing this here? Well, as I'm going to show later in a few slides, we are proposing that these low temperature anomalies are produced by the release and the transport of gas from the magma reservoir to the very shallow, to the surface. And let me start again with the motivation behind this research. Again, we have our magma reservoir, which is active, many processes going on. We have the formation of gas phase, and the gas can escape via permeable flow through the crust. So what is interestingly, if you go to the field and if you install the proper instruments in the flanks of the volcano, I think we are going to do that tomorrow in the field, you will record in many different areas high levels of magmatic CO2, so CO2 coming from the magma. Interestingly, the temperature of that CO2 is very low. It's on the order of ambient temperature. So that means that there has been a change of the temperature of around 3 orders of magnitude. So something is going on with that heat, right? The second thing I would like to highlight here is that, well, in principle, we don't see water vapor being released diffusively through the soil, similarly to the CO2. So that means that probably water vapor is being condensed somewhere beneath the surface. So if this is happening, and through a simple exercise, one can see that 100 tons of water vapor per day, this can lead to a thermal energy of 10 to the 10 to 10 to 11 joule in 1 year, which corresponds to the energy released by a magnitude 4 earthquake. It's not a huge amount of energy, but definitely is not negligible either. So these two processes that came to my mind at some point led to the key question that motivates this. What happens with the heat? So the hypothesis is that diffuse outgassing and condensation in the shallow subsurface can produce changes of the radiant heat emissions of the volcanic flux. And this is the hypothesis that we were testing through the analysis of remote sensing data. I'm not going to explain nothing about the method, but I would invite you to take a look to the paper if you are interested in knowing a bit more about it. Just let me focus on the results for this particular case, Redoubt volcano in Alaska. In the horizontal axis, you have time, The vertical line is showing the initiation of the 2009 eruption. The red line is showing the evolution of the thermal anomalies in the flanks of the volcano with respect to the area around the volcano. And the pinky area is showing the 95% confidence interval. So this shows that from 4 to 6 years prior to the occurrence of the eruption, there was an increase of the radiant heat emissions in the volcano. I'm not going to explain the details for the rest of volcanoes that I'm showing here. Just I would like to highlight that we observed similar patterns independently of the, for these volcanoes, independently of the type of eruption, magmatic in this case, or gas explosions, as we see at the bottom. So the fact that we see similar results independently of the volcano, that is probably telling us, supporting the hypothesis that this is driven by the gas and not driven by a very shallow magma source. These are very new results that we have for the eruption in La Palma. This comes from an updated version of the methodology that we have in that paper. Now we are calculating not only the temporal evolution of the thermal anomaly, but also the spatial distribution of those anomalies. So in this, here you can see this thermal map. Different colors represent different temperatures, and these black squares, they just, this is just a mask because there were wildfires, so we don't want just to get confused with that. What we can see here, well, there was an eruption in last fall occurring somewhere here in a cone here, but interestingly, we observe a thermal anomaly emerging at the center of the caldera that is at the northern part of the island. Sometime after, we start to see that basically the whole island is starting to show some significant thermal anomaly. We discussed with our colleagues from the Canary Islands, and this is consistent with the idea that they also have that from the geochemical point of view, there is a connection, there is some connectivity between the different parts of the island. So one more time, this is supporting the hypothesis that this process is probably driven by gas transport. So the take-home message from this analysis is that we see that volcanoes can increase the radiant heat emissions for years prior to eruption. But what about the processes? We mentioned that briefly, and I'm going to spend just a few minutes talking about this. We are starting to work on different models. So in these models, this is just a 2D axisymmetric model. This is your magma reservoir. This is the shallow crust. And here, if you impose a pressure in the magma reservoir, this is going to drive a transport of gas through the crust. So by solving the transport equations, mass conservation, Darcy's flow, and also thermal energy, thermal equation, heat equation, we are able to explore the temporal evolution of the, we are able to explore the distribution of the thermal emissions in the shallow subsurface as, again, as a result of the transport of gas through the crust. We are interested in exploring what's going on in the surface, which is what I'm going to show in the next slide. So in this plot, the horizontal axis is showing distance, the vertical axis is showing temperature, and different colors represent different values of the different years. So when you move up, you are moving forward in time. So what this is showing is that for realistic values of the parameters, but always with high permeabilities, you are able to produce thermal anomalies of up to 1 degree in timescales of a few years, which is what we are observing in the data. But again, I want to highlight that we observe this behavior only for highly permeable crusts. We can discuss more about it later if you are interested. Otherwise, it's impossible to explain these thermal signals in the timescales that we have. I also would like to mention briefly that we also want to explore this in the field. So last summer, thanks to the collaboration between ABO and ABERT, with Terry, we were able to install a couple of soil sensors at Okmok caldera. So the goal of these experiments, well, this is a proof of concept, and hopefully, once we get some funding, we hopefully can start to compare these remote sensing results with results that we are actually measuring from the ground. Just showing how we install these sensors and this preliminary data that we are starting to receive in Fairbanks and also at Le Mans. And also, just to end, I would like to mention that there are many things going on, many things happening when the gas is moving upwards through the crust. In the case of water vapor, as we said before, we are going to have probably this condensation at some point. So we are exploring that in lab experiments with different colleagues from the University of Alicante in Spain, who are experts on those kind of experiments. And we are starting to see some interesting behavior. Also from some models that my student Claire Puleo is starting to do, she obtained that low temperature thermal anomalies appear also to be consistent with the condensation of steam if that occurs at a few tens of meter depth. But if the condensation occurs at much deeper levels, it's impossible again to explain these thermal signals in these timescales of a few years. So at least we are obtaining some constraint regarding the different processes. I would like just to end here, just remembering that volatile solution controls rheology, short-term evolution, that means eruptive regime, and also the long-term evolution of volcanoes. Also, we find that the gas transport can provide some, is changing something in the volcano, and this provides some explanation to some of the monitoring signals that we can see in active volcanoes. We have many open questions. I just would like to highlight here that it would be very interesting to explore, to better understand what is the interaction between these magmatic gases and hydrothermal systems, not only from the physical point of view, from the physics point of view, as I have done here, but also from the chemistry point of view, where most of you are much more experts than I am. And I'm pretty sure all of you want to know what happens if you go to ski with 40 degrees below zero. This will happen with your face, so I'm happy to take questions.